Imagine a future where problems that would take today's most powerful supercomputers millions of years to solve are cracked in seconds. Imagine encryption systems you trust every day suddenly becoming vulnerable. Imagine a technology so powerful that it could revolutionize medicine, climate modeling, logistics, and artificial intelligence, while simultaneously threatening the foundations of cybersecurity. That future is not science fiction, it is quantum technology. Today, you are going to explore what quantum computing really is, why it matters to you, why governments and security agencies are paying attention, and why you must start thinking about quantum readiness now, not later. When you hear the word quantum, it might sound abstract or overly scientific, but quantum technology simply refers to systems that use the principles of quantum mechanics, the physics that governs the smallest particles in our universe. Unlike classical physics, which explains how cars move and planes fly, quantum mechanics explains how electrons and photons behave. And at that microscopic level, the universe behaves very differently. Quantum technology includes three main domains: quantum computing, quantum communication, quantum sensing. Quantum computing focuses on performing calculations in entirely new ways. Quantum communication uses quantum properties to enhance secure communication. Quantum sensing uses quantum effects to measure physical properties with unprecedented precision. But to understand why this is powerful, you need to understand two strange but fundamental quantum principles. In classical computing, information is stored in bits. A bit can be either 0 or 1. In quantum computing, information is stored in qubits. And a qubit can be 0, 1 or both at the same time. This both at the same time phenomenon is called superposition. Imagine flipping a coin. In the classical world, it lands as heads or tails. But in the quantum world, until you observe it, that coin is both heads and tails simultaneously. This means a quantum computer can explore many possible solutions at once. Instead of trying one path at a time like a classical computer, it can evaluate multiple paths simultaneously. That parallelism is what gives quantum computing its potential exponential power. The second critical principle is entanglement. When two particles become entangled, they remain connected no matter how far apart they are. If something changes in one particle, the other instantly reflects that change. This is not theoretical speculation. It has been experimentally validated. For computing, entanglement allows qubits to work together in highly coordinated ways, dramatically increasing computational complexity. Think of it as a network of qubits acting as one unified system rather than independent units. Together, superposition and entanglement enable quantum computers to tackle certain types of problems far more efficiently than classical machines. How quantum computing differs from classical computing? Your laptop processes information sequentially or in limited parallel threads. Even supercomputers are fundamentally classical machines, scaling speed and size but not changing the logic. Quantum computers operate differently. They do not replace classical computers for everyday tasks like browsing the internet or writing emails. Instead, they excel at solving specific types of complex mathematical problems, such as factoring large numbers, optimization problems, molecular simulations, complex system modeling. These problems grow exponentially harder for classical computers as size increases. Quantum computers approach them differently, leveraging quantum algorithms that exploit superposition and entanglement. This is why quantum computing is often described as disruptive rather than incremental. Why quantum matters for cybersecurity? Here is where things become serious. Modern encryption relies heavily on mathematical problems that are hard for classical computers to solve. For example, RSA encryption relies on the difficulty of factoring very large numbers. Today's computers would take an impractical amount of time to break strong encryption. But quantum computers could change that. There is a quantum algorithm called Shor's algorithm that can factor large numbers efficiently. If sufficiently powerful quantum computers become available, many of today's public key cryptographic systems could become vulnerable. That means banking systems, government secrets, critical infrastructure communications, cloud authentication systems could be exposed if organizations are not prepared. Even if quantum computers capable of breaking encryption are not widely available today, attackers may already be collecting encrypted data in anticipation of future quantum capability. This is often referred to as harvest now, decrypt later. So the risk is not hypothetical, it is strategic. Fortunately, the cybersecurity community is not standing still. Researchers are developing post-quantum cryptography (PQC) cryptographic algorithms designed to resist both classical and quantum attacks. These new algorithms aim to maintain security even against quantum computers, run efficiently on existing hardware, support gradual migration. However, transitioning to post-quantum cryptography is not as simple as updating a password. It requires inventorying cryptographic assets, understanding where encryption is used, updating protocols and systems, coordinating with vendors and partners, testing interoperability. Migration will take years for many organizations. That is why planning must begin now. Quantum computing is not only a cyber threat, it is also a transformative opportunity. In medicine, quantum simulations could model molecular interactions in ways classical systems cannot, accelerating drug discovery. In climate science, quantum models may improve complex environmental simulations. In logistics, quantum optimization could reduce costs and emissions. In artificial intelligence, quantum enhanced machine learning could unlock new capabilities. So, you are looking at a technology with immense upside and significant security implications. That duality is what makes quantum so strategically important. Why future consideration is critical? You may be thinking, quantum computers capable of breaking encryption are not mainstream yet. So why worry now? Because cryptographic migration takes years. Legacy systems are complex. Sensitive data often needs protection for decades. Infrastructure changes require planning and budget cycles. Waiting until a breakthrough is announced is too late. Future consideration means embedding quantum readiness into strategic planning, tracking regulatory developments, monitoring cryptographic standards, engaging with vendors about quantum safe roadmaps. This is not panic, it is prudent risk management. Just like organizations prepared early for cloud transformation gained advantage, those who prepare early for quantum will be resilient. How you should start preparing. Here is what you should be thinking about today. First, understand your cryptographic footprint. Where are you using encryption? What algorithms are deployed? Second, evaluate data longevity. What information must remain secure for 10, 20 or 30 years? Third, stay informed about post-quantum standards and industry guidance. Fourth, include quantum risk in your enterprise risk management discussions. Finally, educate your leadership team. Quantum readiness is not just a technical topic, it is a governance and strategy issue. Quantum technology represents one of the most significant paradigm shifts in computing since the invention of classical digital systems. Just as the internet reshaped society and cloud computing reshaped infrastructure, quantum computing may reshape both opportunity and risk. If you are a leader, architect, or security professional, your responsibility is not to become a quantum physicist. Your responsibility is to understand the risk trajectory, the migration pathway, the strategic implications, the timeline uncertainty, and to ensure your organization is not caught unprepared. Let's recap what you should remember. Quantum technology leverages the strange laws of quantum mechanics to enable new capabilities. Superposition allows qubits to represent multiple states at once. Entanglement links particles in powerful ways. Quantum computing may break traditional encryption methods. Post-quantum cryptography is the defensive evolution. Migration will take time, and preparation must start early. Quantum represents both extraordinary opportunity and serious security consideration. The quantum future is not about fear. It is about awareness and readiness. You are standing at the edge of a technological shift that could redefine computing, security, and global competition. The question is not whether quantum will impact you. The question is whether you will be prepared when it does. If this deep dive helped you understand quantum technology and its security implications, make sure you like this video, subscribe to the channel, and share it with your colleagues. Leave a comment below. How prepared do you think organizations are for the quantum shift? And if you want more strategic insights into emerging technologies shaping cybersecurity and digital transformation, stay tuned, stay informed, stay strategic, stay secure.